Okay, so implicit differentiation. Try each of these and then we'll go through it. Okay, so the first thing is when I derive the first expression over here, right? So part one, I am finding d dx of x squared. So that's going to become 2x using the power rule. When I derive y, it becomes 1 because 1 goes to the front. I use the power rule on y, but because it's not in terms of x, I have to write dy dx afterwards. When I derive 3, it becomes 0, and then I can then make dy dx the subject of the formula, which will be negative 2x, and I'm done. For part 2, derive the first part, which is going to be 20x3 plus 2y, because I'm deriving this, but it's not with respect to x. So I have to write multiply by dy dx, which I'm going to make the subject of the formula, and then minus 0, because 4 is 0. So if I make this the subject of the formula, I will have to move this over to the other side, and I'll get 2y times dy dx equals negative 20x cubed. And so dy dx will be negative 20x cubed divided by 2y, which can simplify into negative 10x cubed over y. Okay. Part 3, when I derive sine, I get cos 3x, but because it's 3x, remember, it's a function inside a function. So using chain rule, I multiply it by the derivative of 3x, which is 3. So that's 3 cos 3x. Deriving 3y becomes just 3 using the power rule, but because it's y, I put dy dx next to it. And deriving 0 is 0. So now I got to make that the subject of the formula. So I'm going to, let's say, move this across. I'll have 3 cos 3x equals 3 times dy dx. And I can divide by 3 on both sides, actually. And that gets me dy dx equals cos 3x from there. Part 4. When I derive e to the x, it stays the same. When I derive e to the y, it also stays the same, but it's not x, so I just write dy dx next to it. When I derive 2x, it's 2. All I got to do is make that the subject of the formula. And when I make that the subject of the formula, I'm going to move this across. E to the y multiplied by dy dx equals 2 minus e to the power of x. And then dividing the whole thing by e to the y gets me dy dx to be 2 minus e to the power of x over e to the y. All right, let's go to the next question. All right, so continue with the implicit differentiation and questions associated with it. The next question, I'm given a curve has the equation x cubed plus 9xy squared equals to 54. And I want to find the gradient of the tangent to the curve at a point, let's say 2 and 3. Okay, so curve is the equation, the following equation, x cubed plus 9xy squared. And I want to find the gradient of the tangent to the curve at this point over here. All right, try that, see if you can do that. Okay. All right. So firstly, when I derive this function, I know that by deriving the x cubed, it's going to become 3x squared. And over here, I've got two functions. So I know for this part here, I've got to use the product rule. And when I do the product rule for this, I treat 9x as a function like u. I treat y squared as function v. And I know I got to get some kind of function that would basically be like u dash v plus uv dash. If I do that in one step, u dash is 9, v is just y squared, right? U dash is 9x derived. And if I plus u, which is 9x, and v dash, which is now deriving y squared to become 2y, multiplied by dy dx, because we're deriving y now, then that should be perfectly in order where I have done it correctly. And on the right, this is all equal to 0, where this is now going to become 0. Okay, I just need to neaten up this now and get dy dx, which is going to be my gradient. Okay, so here we go. So I got 3x squared plus 9y squared plus 18xy times dy dx, which is equal to 0. I can divide everything by 3 all the way across, so I might as well do that now. I could also do that in the next step. So 6xy times dy dx equals to 0. Move everything over to the other side, and I get dy dx equals negative x squared minus 3y squared, all divided by 6xy once I divide that at the bottom. Now that I have my gradient, we want to find the gradient of the tangent to the curve at this point. And guess what? We've got the x and we've got the y value. So you know what? That's perfect. Okay, so I can just change x into 2 and y into 3. X into 2 and y into 3. Right, this was an arrow. Okay, so therefore, my gradient is going to basically be substitution now. And when I put that on a calculator, it'll come to negative 2 over 3. No, it'll come to another number. All right, let's go through, put it on a calculator. At the top, so yeah, you're right, negative 31 over 6 times 2 is 12 times 3 is 36. And that's my final answer for my gradient for this one. Now we're going to pick up the difficulty level now on the next question. Okay. The next question is going to be the following. Using implicit differentiation, I want you to show that dx of a to the power of x is equal to a to the power of x ln a. Okay, so using implicit differentiation, see if you can do that. All right. So in this question here, we have our natural logarithm, and we are asked to derive a to the power of x and show it's equal to the other side. Now, at the moment, we can see that, let's suppose I had to derive. Now, how do I derive, firstly, x as a power? Right? We know x to be the base. we can easily derive that. That's ax to the power of a minus 1. That's normal power rule. But now x is in the power, and these two have been swapped around. This is where implicit differentiation comes in use a lot. So if I make this equal to y, and I go d dx of this function y, so I'm going to say let y equal a to the power of x. And if I'm deriving d dx y, it'll become 1 times dy dx. And if I derive the right-hand side with respect to x as well, so I'm going to go d dx. Well, I actually don't need to. Actually, I'm just going to prove that it's equal to that. So if I derive this, it's going to be dy dx on the left-hand side. Done. Okay. If I look at the right-hand side and I actually see that a to the power of x is here as well, which means that this can be y. Right? So I can rewrite this as y ln a. And I know that if I make ln a the subject of the formula, if I divide this side by y, right? So I divide this whole side by y. So this is y ln a, and I divide it by y on both sides. I'm going to end up getting 1 over y times dy dx equals ln a. And once I have this, I can bring the a to the x back in over here, which will become 1 over a to the power of x times dy dx equals ln a. But I can also bring it into the y. So which means I can actually change this y value into a to the power of x. So what am I actually going? D a to the power of x, which is y, over dx equals ln a. If I move this back up again, I've got d, the derivative of a to the power of x with respect to x, is equal to a to the power of x ln a. Let's have a look at another way of solving this. Let's suppose I've got more simple form. I've got to prove that d dx of a to the power of x equals a to the power of x ln a. If y is equal to a to the power of x and I ln both sides, then I'll end up with that. Using the power rule and bringing x to the front, I get ln a. So ln y equals x ln a, or log y equals log, but natural logarithmics, right? From this here, deriving this whole function, right? So if I go d dx of the whole function, all right, the right-hand side is going to be 1 over y multiplied by dy dx. And on the other side, we know ln a is just a value. So d dx of this, remember a is a constant. So this whole thing over here is a number. So that will simply just become ln a. And then I rearrange that dy dx, it will end up as y multiplied by ln a. And we originally made it equal to that. So that is going to be a to the power of x times ln a. Okay. And that's the best way to solve it. Okay, so this is the method to use. So what did I do? I took whatever's in the bracket, I made it equal to y. I ln both sides. And after I did that, I dx'd both sides using implicit differentiation. And then I made dy dx the subject of the formula. Okay, let's go to the next question. A more difficult question. Let's suppose we try the following. We want to verify that -1 and 0 lies on the curve with equation 3x e to the power of y plus 2x plus 5 equals 4y. And we want to find the equation of the tangent to the curve at -1, 0. Give your answer in the form ax plus by plus c equals 0, where a, b, and c are integers. Okay. Try this, and then we'll go through. Okay, so the first thing from here, I can see that x equals to -1 and y equals to 0. So if I have to substitute it into this equation from the left-hand side, I got the left-hand side of the equation would be given by 3 times -1 e to the power of 0 plus 2 times -1 plus 5. And that'll come to 0. And in the right-hand side, if I put 3 times 0, it will also come to 0. So we can see that, therefore, it lies on the curve. Okay, because the left-hand side is equal to the right-hand side, therefore it lies on the curve. Okay, the second part of the question, we're now saying they're asking us to find the equation of the tangent to the curve. So we know this is going to be y equals mx plus c. The first thing I need to do is first find the gradient m. So I got to derive this function, and I'm going to go and say d dx across both sides of the equation. If I do that on this side here, the first thing I got here is product rule. So I'm going to end up with 3x e to the power of y dy dx. Okay. Remember, for this one here, this is, let's say, u, and this is v. Then this is uv dash plus u dash v, which is going to be 3 times e to the power of y, which just stays the same. And now I've used the product rule, and I'm done with that. Plus 2, the next part. Right, so that's product rule. And then that's 0 equals 4y will just become 4 times dy dx. And I can see dy dx is in 2 parts of the equation. It's over here. It's over here. So let's bring it all onto one side of the equation, or subtract it out, etc., on one side of the equation as well. But before I do that, I'm going to substitute -1 and 0 into this equation. X equals to -1 and y equals to 0. If I do that, I get 3 times -1 e to the power of 0 dy dx. Let's keep dy dx. We can't substitute anything in there. 3e to the 0 plus 2 equals 4 dy dx. And this is at that point, so we can't do that. And this is going to now substitute into this, getting me all of this, and moving this over onto the other side. This becomes 4, and this will become -3 dy dx. Move it across, this will be plus 5 equals 4 dy dx. Okay, continuing from there, I get 5 equals 7 times dy dx. Dividing by 7 on both sides, I get dy dx to be 5 over 7, and that is my m value, which goes into y equals mx plus c. And all I have to do now is substitute. I'm going to take this equation now and substitute 0, -1 in there. The other way around, -1 and 0. And I would get if x is equal to negative 1, y equals 0. So this will be 0 equals to 5 over 7 times negative 1 plus c. That's negative 5 over 7 moving over becomes 5 over 7 equals c. And so therefore my final equation is y is equal to 5 over 7x plus 5 over 7. All right, if I'm doing this correctly, I need to get it in this form. So I would end up multiplying everything by 7. And when I multiply everything by 7, my final answer actually ends up as such. 7y equals 5x plus 5. And we want everything on the left-hand side. So therefore, that will become the final answer, if I can put it in here, would be moved across completely. All right, so minus 5x plus 7y minus 5 equals 0. So I can see A would be equal to minus 5, B will be equal to 7, and C will be equal to minus 5, straight from that part over there. Okay. Let's try the next one now. Still sticking with this, but extending it into the next question now. I want to show, let's see if we can try this one here. I want to show that the derivative of a to the power of kx is given by k a to the power of kx ln a. Okay. All right, so for this question here, the first thing I'm going to do is I'm going to let y equal a to the power of kx. And then I'm going to ln both sides. So ln y equals ln a to the power of kx. And I'm going to move that power to the front. It's going to become kx ln a. And I've got ln y over there. The next thing I want to do is derive the entire function with respect to x. So this would be d dx, and this side would also be d dx. In this case, on the right-hand side, remember that over there is a constant. It's just a number, as well as k, just a number. So when I derive this, x will just simply disappear, leaving me with k ln a. On the right-hand side, 1 over y times dy dx, because I do not know, I'm not deriving with respect to x. I am deriving with respect to x, but I'm not deriving x, I'm deriving y. So we put dy dx. Okay. Now moving y across, I can isolate dy dx, and it'll become y times k ln a. So dy dx becomes yk ln a. And from this here, I can substitute y equals a to the power of kx back in there. And so dy dx will become a to the power of kx times k ln a. I could move the k to the front and make it look like the initial question over there. Very similar to the last question, but just a little bit slightly different. Okay, moving into some very difficult types now. Very difficult type of question. A curve is described by the equation ln y plus x squared y squared equals to 9. And we want to show that the tangents of the 2 points on the curve where y equals to 1 meet at the point 0 and 37/19. We want to show that the tangents of the 2 points on the curve where y is equal to 1 meet at, so you can have a curve and you have another curve, or 2 points of the same curve. All right, if you get two tangents, we're saying that 2 points on the curve where y is equal to 1 meet at the point. So there's tangent like that, another one, and meets at some point 0, 37/19. These are hypothetical tangents. All right. Okay, think about the concept of tangents. Over here, we're looking at gradients as well. Okay. All right, so for this one here, the first thing we got is we know that if y is equal to 1 and I substitute it in there, it will produce ln 1 plus x squared equals 9. And then therefore, I can say x squared is equal to, now we know ln 1 is 0, so x squared will equal to 9. And when I square root both sides, I will get x equals to plus minus 3. Now that I have the x values, I can then say, okay, well, I've got two values. I've got 3 and 1, and I've got -3 and 1. And those are the 2 points. Now I'm going to derive this function in order to get the gradients. Okay, so I'm going to take d dx of the left-hand side and d dx of the right-hand side. When I derive the left-hand side ln y, it'll become 1 over y times dy dx. When I derive x squared y squared, it'll become, using u and v, let's say we go x squared times 2y times dy dx, where we're going u v dash, plus u dash v will be 2x times y squared. And then this is equal to 0 because 9 derived to 0. So now I've got dy dx over here, and I've got dy dx over here. I need to isolate it. If I isolate it, I've got to move this over. It'll become -2xy squared. Factorize it on the left-hand side out of these two terms over here. And that'll become 1 over y plus x squared times 2y. And then divide both sides by that. So dy dx will end up as -2xy squared, all divided by that whole function. So 1 over y plus x squared times 2y. So this is the derivative. This is dy dx, the gradient. Now that I have the gradient, at 3, 1, I can substitute. So at the point 3, 1, if I substitute x equals 3 and y equals 1 into this equation, into this expression, my dy dx ends up as -6/9, 19. When I substitute -3 and 1 in here, my dy dx ends up as 6/19. All right, so I've got these two gradients now. Okay, at 3, 1, my dy dx is going to equal to -6/19, and at -3, 1, my gradient dy dx will equal 6 over 19, positive 6 over 19. Using y equals mx plus c, I can substitute that in there for my m value, and then change that into x and that into y, that in x and that into y. And once I do that, I will end up with the equation y equals negative 6 over 19x plus 37 over 19, and y will equal 6 over 19x plus 37 over 19. And well, look at that, they both have the same y-intercept. So immediately I can tell from this, which saves me time to do simultaneous equations or anything else. The y-intercept is where they meet, and so therefore the intersection point or the tangents meet at the y-intercept.